Hello, everybody, and welcome to this week's lesson. This week, we're continuing talking about functions. We're going to talk about a couple of special types of functions, linear functions and proportional relationships. So for this lesson, you're going to need pencil and paper. You might find it helpful to have last week's lesson notes with you. You'll need your welcome packet because we're going to use your formula sheet, and you might find a calculator useful too. And we're going to start with this warm-up question here. Go ahead and pause the video, take a second to read through it, give it a try, and then when you're ready, come back to the video and we're going to work through it together. Okay. So the question says, does the following represent a function y or y not? So we've got this list of coordinate pairs here. So this list of x, y values. We want to remember that when we have a list of numbers like this, the first number in the pair is always the x or the input, and the second number is always the y. So we have this list of inputs and outputs. All right, so does this list show a function? Well, what is a function? A function is a relation between input and output where each input, so each x, has exactly one output, exactly one y. So is that true for this list of inputs and outputs? No, it's not, right? Because if we look at the first two coordinate pairs here, we see we've got an input of 1 that gives us an output of -2. But then that input of 1 is also giving us an output of +2. So we've got one input that's giving us two outputs. And then actually the same thing is happening again with 3, right? We've got an input of 3 that's giving us an output of -4 and an output of +4. So this relation does not meet the definition of a function. So no, it does not represent a function because each input has more than one output. All right, so our learning goals for this week, a couple of these are continued from last week. So we're going to continue using algebra related vocabulary to discuss and explain problem solving. We're going to identify linear functions represented in multiple ways. Identify proportional relationships represented in multiple ways. We're going to write linear equations to represent context. We're going to determine the slope of a linear function when represented in multiple ways. And we're going to get a little bit of practice with evaluating a linear function. So things to focus on here this week are identifying linear functions, identifying proportional relationships, and determining slope. Those are kind of our three main things to focus on this week. All right, so we're going to do a little remembering from last week that we started doing with our warm-up problem. It's very important that as we discuss special types of functions that we keep in mind what is a function. So we want to remember that a function is this relationship between two variables. It's a relationship between input and output, where there is exactly one output for each input. So if you think back to our toaster from last week, right? You put one piece of bread into your toaster, you expect to get one piece of bread, one piece of toast out of your toaster, right? You don't expect to have a magical toaster that gives you two pieces of toast, one piece of bread in, one piece of toast out. And we've got the example on the screen here that we looked at quite a bit last week as well. So this idea of the relationship between hours that you put into your job and the amount of dollars that you earn. So Robin earns $15 per hour. That means that to calculate her earnings, she would do $15 an hour times the number of hours she works, right? That's the input. And then that would tell her her total earnings. That would be her output. She puts time into her job and she gets money out of her job. So the input is hours, the output is dollars. And we see that in the graph here as well, right? So along the x-axis, along the horizontal axis, we have the hours that she's working. And along the y-axis, we have the dollars that she earns. So when she works for 0 hours, she makes $0 because that's the way the world works. When she works for 1 hour, she makes $15 and so on along this red line here. All right, so linear functions. A linear function is a function that has a constant rate of change or slope. So that means it makes a straight line when you graph it. And you can see, right, the word line is hiding inside of the name, right? Linear functions basically means it's a line. If you're looking at the equation of a linear function, the variables will have no exponents or roots. The input variable will not be in the denominator of a fraction. So there shouldn't be anything too crazy going on with the variables. You should just see a y and an x. You shouldn't see any exponents or roots, nothing like that. So when you're looking at the equation, there should be no exponents or roots. Input variable is not in the denominator of a fraction. Okay, and we said that a linear function has a constant rate of change or slope. And technically what that means is we're talking about the ratio of change in y to change in x. So slope, which we're going to talk about in a lot more detail in a few minutes, but slope is the ratio of change in y to change in x. So it is a comparison of the change that happens in the output, the change that happens in the output to change that happens in the input, right? If we remember that the word ratio means comparison. So let's look at some examples. Actually, before we look at some examples, why do we care about linear functions? Well, one reason we care about linear functions is they show up a lot on the GED math test. So it's really important to be familiar with them and to get lots of practice with different types of questions relating to linear functions, because you will almost definitely see something relating to them on the GED math test. But another reason why we care about them is linear relationships between things are very common. Just a lot of things that you encounter out in the world have linear relationships or basically linear relationships. So I've got a few examples of that on the screen here. If we think about the relationship between time and distance, if you're traveling at a constant speed for a little while, the amount of time that you travel for will be linearly related to the amount of distance that you cover. If you are someone who works in sales on commission, you probably earn a percent of the sales that you make. That is a linear relationship. The amount of commission that you earn will be some percent of the sales that you make. That is a linear function. And the relationship between taxi fare and distance driven is also basically a linear function, a linear relationship. The amount that you're charged is based on the distance that the taxi driver drives you or the Uber driver drives you. All right, so now let's look at some examples. We want to keep these characteristics in mind here of a linear function. So we want to remember that it makes a straight line when graphed. The variables have no exponents or roots, and the input variable should not be in the denominator of a fraction. So let's start with this first equation right here. We'll start with this equation, y equals 2x. So is it linear or nonlinear? Well, I look at my variables. I don't see any exponents or roots. Nothing is in the denominator of a fraction. So this is a linear function. Let's look at this second equation. says f of x equals 1.5x minus 7. So again, I've got my input variable, my output variable and my input variable. There's no exponents, no roots, nothing crazy going on with those variables. So this also would be a linear function. Now let's go over to the other side of the screen here. Let's look at this next equation, y equals x squared. So this is an example of a non-linear function. It is not, we know that it's nonlinear because the x has an exponent, right? It's not just x, it's x squared. So this would be a non-linear function. And this fourth equation, y equals 3 over x, or 3 divided by x. Well, we see that the input variable is in the denominator of a fraction. So that would also disqualify it from being linear. It's going to make it non-linear. All right, next let's look at these graphs. So let's look at this graph, this first one on the left side here. This is showing us a linear function. It makes a straight line. So this would also be a linear function. And the second graph over on the right side, it does not make a straight line. So it is nonlinear. It's a curve, not a straight line. Okay, so we looked at the equations, we looked at the graphs. Now let's talk about these tables. For these tables, we want to think back to the actual definition of a linear function, where it's a function with a constant slope or a constant rate of change. So to determine whether or not the rate of change is constant, what we would do is we would look at the change that's happening in our input variables. So for example, on the left-hand side here with this table, if I look at the input column, when I go from 0 to 1, that is a change of 1 or positive 1. Now, if I come over here to the output, when I go from 1 to 2, that is a change of 1 or positive 1. And so, right, we said the rate of change is a comparison of change in y to change in x. So I just determined here that this ratio should be 1 to 1. The change in y was 1, the change in x was 1. And let's make sure, we want to see, does that ratio stay the same throughout the whole table? So when I go from 1 to 2, that's a change of 1. When I go from 2 to 3, that's a change of 1. So I get the same ratio, 1 to 1. When I go from 2 to 3, that's a change of 1. And 3 to 4 is a change of 1. So again, I get this ratio of 1 to 1. Now, it's not important that all of the numbers are 1. It's important that all of these ratios are the same. 1 to 1, it's the same throughout. So this is an example of a linear function because the change that's happening stays the same. It's the same change every time. Now let's go over to this other table. If we look down the x column, we'll see that it's the same change that's happening each time. Each time we go up an x value, we're going up by 1. But now when we go over here and look at our outputs, 1 to 2 is 1, so my ratio is 1 to 1. But then 2 to 5 is 3, so that ratio is 3 to 1. And then 5 to 10 would be a change of 5. We get a ratio of 5 to 1. So when we look at the change that's happening in our x and our y, we got this ratio of 1 to 1, which is not the same thing as 3 to 1 or 5 to 1. So we have a non-constant rate of change. We have a non-constant slope here, which would make it non-linear. So actually all of these examples on the right-hand side are examples of non-linear functions. And on the left-hand side here, we have examples of linear functions. So now I'm going to give you a chance to practice that a little bit. So take a moment to pause the video, look at these three functions, and tell me, or tell yourself, write down on a piece of paper whether each one is linear or nonlinear. And when you think you've got it, return to the video and we're going to go through it together. So number one, we're given this table. And so in order to determine whether this table shows a linear function, we are going to compare the change that's happening in the input with the change that's happening in the output. So my inputs, I'm going from 0 to 1. That's a change of 1. 0 to 1 is a change of 1. So that first ratio is 1 to 1, the first slope, 1 to 1. Going from 1 to 2 is a change of 1, and 1 to 4 is a change of 3. So now we're getting this ratio of 3 to 1. 1 to 1 is not the same thing as 3 to 1. So right away we can tell that this is a non-linear function. All right, now let's take a look at number 2. When we look at this graph, is it a straight line? Yes, it is. So this is showing us a linear function. And number 3, we have an equation. It says f of x equals negative 1/2 x plus 4. I don't see any exponents or roots on my variables, and none of my variables are down in the denominator of a fraction. So this also is a linear function. All right, so now let's talk a little bit more in depth about slope. When you have a linear relationship between x and y, that means that each time x changes, y will always change in a constant amount. So it will always change in the same amount each time x changes. And so the way that we measure the amount of change, the way that we talk about the amount of change, is we make a ratio of the change in y to change in x. And that is what slope is. Another way you can think of slope is that it's a measurement of the steepness of the line that you're making. So a very steep line will have a higher slope. You'll get a bigger number. And a not very steep line, sort of gently sloping line, will have a smaller slope. You'll get a smaller number. So slope it basically tells us how big is the slope, right? How steep is the line that we're talking about. Another thing to keep in mind is that a negative slope tells you that you're sloping downwards. A positive slope tells you that you are sloping upwards. So there are many different ways that you can determine or calculate the slope depending on the way the function is presented to you. So you can figure out the slope by looking at a graph. You can figure it out by looking at a table, which we've already started doing. You can figure it out by looking at a pair of coordinates, so 2 points. For that, you would use the slope formula from your formula sheet. Or you can do it by just looking at an equation of a line. So what we're going to do now is we're going to look at an example of each of these things and how we would figure out the slope. All right, so let's say we are looking at a graph. How would we figure out the slope of this line? So the line is the line that we're talking about is the red line that is sort of sloping upwards here. Well, right away, since it is sloping upwards, we would expect it to have a positive slope. Right, lines that go up like that have positive slopes. But how do we get the actual number? So if you are looking at a graph, and especially if it is a graph where you've got nice clear whole numbers, the grid is on there for you, then it will be a pretty simple job figuring out the slope just using the graph. If the graph is dealing with like bigger numbers or decimal numbers, it might not be as straightforward to figure out the slope with just the graph. But if the numbers on the graph are clear and you can find some points where you definitely know what the numbers are for those points, then you can figure out the slope with the graph. So what you do, first thing you do is you pick a point on the line. So I'm going to pick this point here. The next thing you do is you pick a second point on the line. And you want that point to be further to the right. So we're working left to right here. So I'm going to pick this point. And the points you pick do not matter as long as they are points on the line and they are points where it is clear to you what the value of those points are. So you want to try and pick points that are definitely whole numbers. Like here, I can see this point is lined up with -3 and it's lined up with -5. You probably wouldn't want to pick a point that's like floating in the decimal area here, right? So this point I just drew would be like -3 point something, but we wouldn't be sure what it is. So you don't want to do that. You want to make your life easy and pick a point that has nice whole numbers. Let me get rid of that extra point there. Okay, so we have picked out our points. And now to determine the slope, what we're going to do is we are going to travel from our first point to our second point along the grid line. So the next thing you're going to do is you're going to determine how far up or down and how far over you need to go to get to the second point. So if I start here, I would need to go up 2 and then over 1 to get to the next point, to get to the second point. And so my slope, remember slope compares, right? Slope, which is sometimes abbreviated with the letter M, is a comparison of the change in Y, so the vertical change, to the change in X, the horizontal change. And so I just discovered that to go from one point to the next here, I had to go up 2, my vertical change was +2, and I had to go over 1, my horizontal change was 1. So I get the slope of 2 to 1, which we could then simplify to just 2. So we find that this line has a slope of 2. That means each time we increase our X by 1, our y is going to increase by 2. And we can see that that's true all along the line here. I can sort of start creating this little staircase where I go up 2 over 1, up 2 over 1, up 2 over 1, up 2 over 1, right? That pattern will always keep me following that line. Now, what if you picked different points to start out with? Would you still end up with the same slope? Yes, you would. So let me show you. I'm going to pick some different points here. Let's pick this point and this point. So if I start here, to get to the next point, I would go up, 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 up. And then I would go over to get back to it. So I just went up 1, 2, 3, 4, 5, 6 spaces. I went up 6 and I went over 1, 2, 3 spaces. And so I get this slope of 6 to 3, 6 over 3, which will simplify to 2. So I end up with the same slope, no matter which points I choose, as long as they are points on the line, you will end up it will end up simplifying to the same ratio or the same number at the end. And again, that letter M is just a variable that's sometimes used to represent slope. So instead of writing the word slope, you can just use the letter M and people will know what you're talking about. Okay, so now let's say we are looking at a table. If you're looking at a table, how could you figure out slope? Well, we already saw how to do this, but let's do it again. Let's do it with some different numbers here. So let's start with -2, -1. And then we're gonna jump a little bit. We're gonna go to 1 and 2. And we're gonna start at 5, 3, -1, and -3. Okay. So now let's determine what the slope is for our table. So we want to remember that slope is a comparison of change in y or change in output. In this case, it would be change in f of x. We want to remember that y and f of x are basically the same thing. To change in x. So I'm going to start figuring out what changes are happening. So let's start by looking at change in y, since that's the number that should go on top of our ratio. It's the number that should go first. So when I go from 5 to 3, that is a decrease of 2, right? To go from 5 to 3, you're decreasing by 2. So to show that it's a decrease, we would say that that's a change of -2. We're going down by 2. And then going from -2 to -1, that is an increase of 1, right? We're going up by 1. So I get this ratio of -2 to 1. Let's see if we get the same ratio if we do different pairs of points here. So going from 3 to -1. How big of a change is that? Well, going from 3 to -1 would be going down by 4. So we would say it's a change of -4. And going from -1 to 1, that is an increase of 2. We get 2 on the bottom. Now, if you think back to our work with positive and negative numbers, Oops, just press some wrong buttons there. If you think back to our work with, no, not our work with positive and negative numbers. If you think back to our work with equivalent fractions, we should know, right, that -4/2 is equivalent to -2/1. Those two fractions or those two ratios, they really mean the same thing. Let's try another pair of points here just to see if we can get another equivalent ratio. Let's go from 5 all the way down to -3. So 5 to -3, that is a decrease of 8. That's going down by 8. And going from -2 to 2, that is an increase of 4. So we get this ratio, this slope of -8/4, which again would just reduce to -2/1. All three of these ratios will reduce or simplify to -2/1, which we can then just simplify even further. We can call it -2. So this linear function has a slope of -2. It means each time we move over 1 in the x direction, we're going to go down 2 in the y direction. So down 2/1, down 2/1. So this is another example you can see where it doesn't really matter what points you choose to calculate your slope with, as long as they're points on the line that you're talking about, as long as they're part of the function, you will arrive at the same slope, right? Because the whole point of a linear function is that the slope is constant. It doesn't change. So no matter what 2 points you pick, it should give you the same slope. All right, so next let's talk about determining the slope using coordinate pairs. So this is a type of problem that you might encounter on your test where you're given a pair of points and they say determine the slope of the line that passes through these points. So the reason why they can ask a question like that is that you only need 2 points to name a line or to specify the location of a line. So I could put 2 points down on the screen here, and the line that I draw through those points will be different from a line that I draw through other points. So I could draw other points in a different location on the screen and I will get a different line. So all you need to like define or name or tell the location of a line is 2 points. And we can use those 2 points to calculate slope. So we want to remember that slope means change in y. To change in x. And now this is where you could use your formula for slope from your formula sheet. On your formula sheet, you will see a formula down towards the bottom, like the bottom quarter of the formula sheet. You'll see something that looks like this. It'll say formula for slope of a line. And you'll see m equals y2 minus y1 over x2 minus x1. So that is the formula that you can use if you've got 2 coordinate pairs or 2 points and you're trying to calculate slope. Now, if you kind of remember what slope means, you shouldn't even really need that formula because you know that all you need to figure out is the change that's happening with your y values and the change that's happening with your x values. So you're subtracting your y's and subtracting your x's. So that's what we're going to do here. We're going to remember that x's come first in our coordinate pair and y's come second. So we've got our 2 points, our 2 x values, and our 2 y values. So I'm going to subtract my y's. I'll do 2 minus 4 and subtract my x's. So 3 minus -2. 2 minus 4 is -2. 3 minus -2 is 5. So we get the slope of -2 over 5. And usually if you have a negative sign in your ratio like that, we would pull it out front. So we just say -2 over 5. Can you simplify this ratio any further? No, you can't, right? You could change it into a decimal number if you wanted to, but you can just leave it in ratio or fraction form like this. What would happen if you flipped around the order of those points, right? So I started with my second point first, right? The 2 and the 3 first, and then I subtracted the first point. Would you get the same answer if you did it in the opposite direction? So if I did 4 minus 2, and then if I did -2 minus 3. So 4 minus 2 is 2. -2 minus 3 is -5. We get 2 over -5, which when we bring that negative sign out front gives us the same slope. So either way, really no matter which order you do it in, you arrive at the same answer for the slope. What this slope is telling us is that if you were to graph this line, what you would be doing is you'd be going down 2 and then over 5, down 2 over 5, down 2 over 5, and that would create this line with that negative slope. All right, and the last way that we're going to talk about for determining slope is by looking at a linear equation. So many times when you are given a linear function or a linear equation, it will be something that looks like this, where you have your y or your output is equal to some number times x plus or minus some other number. Now this way of writing a linear equation, it has a special name because it's very common, and it's called slope-intercept form. This is actually on your formula sheet. So you'll see if you look at your formula sheet right next to where you see the slope formula, you will see something that says slope-intercept form of a linear equation. So slope-intercept form always looks like this: y equals some number times x plus or minus some other number. And it is called slope-intercept form because that number that is being multiplied with the x, that number that's right in front of the x, is the slope. And the number at the end, the number that's being added or subtracted at the end, is the y-intercept. We're going to talk more about intercepts next week. But the y-intercept is really just telling you where the line is crossing the y-axis, right? So intercept means to like cross or come together. So the y-intercept is where this function is crossing or touching the y-axis. So when you're looking at a linear equation like this, you see, okay, this is in slope-intercept form, and I look for the number that's being multiplied with x, and that's the slope. So the slope of this line is -4. That means you go down 4 each time you go over 1. So you'd be going down 4 over 1, down 4 over 1. And that would create the line. Okay, so let's get some practice here with determining the slope. What I would like for you to do is I'd like you to pause the video, and for each of these 4 linear functions, I'd like you to try calculating or determining what the slope is. And then when you're ready, you can come back to the video and we're going to work through it together. So number one, we've got a table. For each of these, we want to remember that slope is change in y compared to change in x. So for number one, if I look at my y's first, I'm going from -4 to -2. So I'm increasing by 2. And then -2 to -1, I'm increasing by 1. So it looks like my slope is going to be 2/1, which is just 2 when you simplify it. But let's check and make sure that we get the same thing each time. So -2 to 0 is an increase of 2. -1 to 0 is also an increase of 1. So I got the same thing. And I will get the same thing again if I keep going. Even if I picked different points, so if I went from -4 to 2, I would get an increase of 6. Going from -1 to 1, I would get an increase of 3. 6/3 will reduce to 2/1. So no matter which pairs of y's and x's we pick, we get this ratio of 2 to 1, which simplifies to 2. So this line has a slope of 2. All right, number 2, we've got a pair of points. So we're basically going to do the same thing we did in number 1. We're going to determine the change that's happening with our y's. And we're going to compare that to the change that's happening with our x's. So 6 minus 1 is 5. And 4 minus -1 is also 5. So we got 5/5, which reduces to 1. So this line has a slope of 1. Now let's look at number 3, which is a graph. So when you look at the graph, you might see that there's 2 points that are already kind of picked out for you on this graph. You could use those points if you'd like to. Let's go ahead and use them. So if I start at this point, I would need to go up 2 spaces. So I'm going up 2. And then I would need to go over 2 spaces to get to the next point. So over 2. So I get this ratio of 2/2, which again will simplify to 1. And if you take a second look at that line, you will actually see that all along the line, you can go up 1 over 1 and get back to the line. Up 1 over 1, up 1 over 1, up 1 over 1, up 1 over 1. Right, so that's the slope, comparing the change in y to the change in x. And finally, for number 4, we have an equation. We see this equation is in slope-intercept form. And so we can pick out the slope as just being that number that's multiplied with x. So the slope of this line is -3/4. All right, and that is how you calculate slope by looking at a table, a pair of points, a graph, or in a linear equation. So the last idea we're going to talk about today is proportional relationships. Now, we have done quite a bit of work with proportions already, and this is just a continuation of that work we've done with proportions. So a proportional relationship is a special type of linear function. So it's a special type of linear relationship between 2 variables, between 2 things. So what's special about proportions or proportional relationships is that the graph is a straight line through the origin. So proportional relationships always include the point 0, 0. It's never going to be a line that's like up here, crossing the y-axis, up here somewhere. It's got to be at the origin, at the point 0, 0. Right, so the origin is that central point. And because the line is intercepting the y-axis at 0, it has this y-intercept of 0. Since the y-intercept is 0, it's nothing, right? The y-intercept is 0. 0 means nothing. And so usually we'll see that a proportional relationship will have an equation that looks like this, y equals kx. Now, k, you might notice, is really doing the same thing. It's in the same spot as m was before when we were talking about linear equations. Why do we switch from m to k when we're talking about proportional relationships? Just to keep it interesting, right? But the k is really doing the same thing that the m is doing. It's saying it is holding the place of the slope. So k, it is a constant, it's a non-changing number. It's a comparison of y to x, and you can think of it as the slope, the rate of change. In the case of a proportional relationship, it also happens to be the unit rate or the constant of proportionality. So that is something that's special about proportional relationships, is the slope is a little bit easier to calculate. Instead of worrying about change in y over change in x, you can do a little shortcut. And you can just pick any xy pair on the line and do y over x. That will give you your slope or your constant. So again, why do we care about proportional relationships? Well, one reason is they show up a lot in the test, right? So you will definitely see questions relating to proportional relationships on the GED test or any other like college prep related tests that you're preparing for. But they're also very common types of relationships, right? All of those examples that we talked about when we talked about solving proportions or writing proportions, those were all examples of proportional relationships. And so they're very common, and it can be helpful to be comfortable working with them and representing them in different ways. So, for example, this situation that we've talked about with Robin earning $15 per hour, right? We said for last week, first thing we said was it's a function. And then at the beginning of the lesson today, we said it's a linear function. But now we can actually see that it is a proportional relationship. So it's this special type of relationship between input and output. So we know it's a proportional relationship because when Robin puts in 0 hours at work, she makes $0, right? So it is a straight line through the origin. It is a proportional relationship. So let's get a little bit of practice with identifying proportional relationships here. Number one, we're given a table. First thing we want to make sure is it linear? So it should be a linear relationship. And then the second thing we want to make sure is that it goes through the origin. So we want to check and make sure it's linear. And it should go through the origin. It should include the point 0, 0. So let's see if that's true for number one. Let's first make sure it's a linear relationship. So going from 0 to 1 is an increase of 1. 0 to 3 is an increase of 3. So I've got this ratio of 3 to 1. 1 to 2 is a change of 1. 3 to 6 is a change of 3. So I get the same ratio, 3 to 1. 2 to 3, change of 1. 6 to 9, change of 3. Same ratio again. So I've got a constant rate of change. I've got a slope of 3. So this is linear. Does it go through the origin? Yes, it does. It includes the point 0, 0. So this is a straight line through the origin. So we would say, yes, this is a proportional relationship. All right, now looking at number two, I see a straight line that goes through the origin. And so I would say that this is a proportional relationship. Number 3, is this a proportional relationship? No, it is not. Right, so we've got this equation, y equals 3x minus 2. This is a linear equation. However, it's this minus 2 that makes it a non-proportional relationship. This is telling us that if we were to graph this line, instead of crossing the y-axis at 0, which is what it has to do if it's proportional, it's going to cross the y-axis at -2. So it's going to be shifted down to -2. So if this equation had just said y equals 3x, that would be proportional. That would be a proportional relationship. But since it's actually crossing the y-axis at -2, it is non-proportional. So it is a linear equation, just doesn't have to happen to be a proportional relationship. And next week, we're going to get a lot more practice with proportional relationships and linear functions. We're going to look at a lot more real world examples of proportional relationships, and we're going to look at comparing different proportional relationships and linear functions. So you're going to see a lot more of these next week and a lot more examples. So we're going to wrap up today with a couple of practice problems relating to our linear functions and proportional relationships. Number 1 says Carlos is renting a lawnmower for the day. He must pay $15. He must pay a $15 rental fee plus $2 per hour. Complete the table below, then choose the equation that best represents the situation. So let's see here. Let's look at our table. I see we've got an input of hours and an output of total dollars. So how much he has to pay. So it looks like we're going to calculate how much he has to pay based on the number of hours he rents this lawnmower for. So he has to pay $15 no matter what, right? $15 just to rent it. And then it's $2 per hour. So if he rents it for 1 hour, that's going to be $15. And then it's going to be plus $2 for the 1 hour. So altogether, it's going to be $17 if he rents it for 1 hour. It sounds expensive to me, but maybe it's a very fancy lawnmower. All right, what if he has it for 2 hours? Well, it's going to be $15 rental fee, and then it's going to be $2 an hour for each of those 2 hours. So 2 times 2. 2 times 2 is 4, right? So he'll have to pay $4 plus 15. Gives us $19 altogether. If he rents it for 3 hours, well, $15 and then $2 an hour times 3 hours. 2 times 3 is 6 plus 15 would be $21. 15 an hour plus $15 plus $2 an hour times 4 hours. Well, you can maybe see that there's a pattern starting to emerge here, but this is going to be 2 times 4 is 8, 15 plus 8 is 23. You might notice, right, that each time we go up an hour, we're going up by $2. And so I would expect this value to be 25, but let's double check. $15 rental fee plus $2 an hour times 5 hours. 2 times 5 is 10, plus 15 is 25. So we actually just discovered here that the slope of this relationship is 2, right? It's The output, the y, is going up by 2 each time the input goes up by 1. So the slope of this relationship is 2. Each time he does 1 more hour with the lawnmower, he has to pay $2 more. Okay, so we've got our table all filled in here, 17, 19, 21, 23, and 25. Now let's figure out the second part of this question. Let's choose the equation that best represents the situation. So let's think about what we did here with our calculations to figure out y, or the total amount that he has to pay. Well, each time we did 15 plus the hourly rental fee, right? So we know that we're going to be adding 15 in there. And if we look at choice B looks pretty darn close to what we were doing when we were calculating his bill, right? We've got that $15 fee, and then we're adding in that hourly rate. So choice B is saying to calculate the total bill, do $2 an hour times the number of hours plus $15. All right, and then on to our last problem for today. It says Joe sews 12 masks, not 2 masks. Joe sews 12 masks in 3 hours. If she sews at a constant rate, choose the equation that represents the relationship between hours and masks sewn. All right, well, let's think about this. 12 masks in 3 hours. She's sewing at a constant rate. So let's first think about, what is her hourly rate? What is her unit rate? So how many masks is she sewing per 1 hour? Well, that would be 12 masks divided by 3 would give us 4 masks per hour. So she's sewing 4 masks per 1 hour. So we could say that the slope, or the rate of change for this relationship, is 4. Right, so if we wanted to figure out how many masks she's able to make in blank hours, we would take the number of hours and multiply it by 4 masks per hour. So that means that the number of masks she makes is equal to 4 masks an hour times the number of hours. And so we would choose answer C. This is an example of a proportional relationship. All right, guys. Well, thank you very much for joining me in this lesson this week. Like I said, next week we are going to continue talking about linear relationships and proportional relationships. We're going to look at more examples. We're going to be comparing different relationships and like how changing the numbers changes the way that the graphs look, all that kind of stuff. So take a look at your homework for this week. Let me know if you have any questions, and I hope I will be talking to some of you very soon. Take care.